So ladies and gentlemen, in this session we want to talk about two things. The first one are elastic properties of rocks, and here it's essentially the Young's modulus and the Poisson's ratio we are going to talk about. And then in a very important section we are going to talk about parameters and factors that control the strength, the shear strength of rocks. So first to the elastic field, to Young's modulus and Poisson's ratio, and in order to understand these two parameters we need to talk about sign conventions, and here it's particularly for the compressive stress. Compressive stresses are always given in positive values, whereas tensile, that means pulling stresses, are given negative values. These are not mathematical positives and negatives. These are rather conventional ones in order to distinguish these two kinds of stresses, which otherwise might have identical magnitudes. We have learned that stresses can cause strain, and contractional strain in response to compressive stress would give a negative value, and we have talked about that before earlier in this course, how these negative values come about. Otherwise, extensional strain would be assigned positive values, and strain is a unitless number, whereas stress is given in pascals, or in geological systems rather in megapascals. So let's have a look at Hooke's law and Young's modulus. They both already came up in the last lectures. Hooke's law simply says that the differential stress is proportional to the differential stress times the Young's modulus, which is a physical property of rocks, because rocks can be more or less elastic, and Young's modulus describes this factor, this material constant. Young's modulus itself you can define just by rearranging this equation, Hooke's law. Young's modulus is given by the differential stress over the elastic contraction. That means also here is a very simple relationship, and as we just have said, elastic strain is dimensionless. Differential stress is given in megapascals. What these two equations, Hooke's law and Young's modulus, simply describe is how much stress is required to achieve a given amount of length parallel elastic shortening in a given rock type. And yeah, please keep in mind, we are not talking about permanent strain, we are talking about elastic strain. And Young's moduli describe this elasticity of rocks. Let's make an example. Young's modulus, as we see here, can be expressed in differential stress over strain, and the strain, as we know here, if it's contraction, would be a finite length minus the original length over the original length. For instance, we are shortening a body that is 100 centimeters long to 99 centimeters, which would be a shortening of 1%, and because we are talking about a shortening, this would be negative. In numbers, that would be minus 0.01. Now let's assume there is a specific rock with a specific elasticity where we need 250 megapascals to achieve this 1% of shortening. And according to the definition for Young's modulus, the Young's modulus in this case would be minus 25,000 megapascals. So now let's consider another rock where the same amount of shortening, this 1% shortening, requires 800 megapascals to be achieved. This rock would have a Young's modulus of minus 80,000 megapascals. So clearly the first one is more elastic than the other one, because it takes less stress, compressive stress, to shorten elastically by a percent compared to the other one. Let's have a look here at a table which is taken from Davis and Reynolds' textbook. Here are various rocks listed, and we see here marble or limestone would have a relatively high elasticity. So if it comes to Young moduli, high values would describe rather elastic material, whereas low values would describe rather stiff material that has a very low elasticity. Let's talk about Poisson's ratio and the Poisson's effect. The Poisson's ratio is simply described by the lateral bulging during length parallel shortening, and here Poisson's ratio is simply defined by lateral strain over longitudinal strain. The negative value is always used because we are talking about contraction. So a rock with a low Poisson's ratio would respond to length parallel shortening, elastic shortening, with only minor elastic lateral bulging, and that means the rock will be under stress because the stress is not released, is not compensated by lateral elastic strain. And this is a potential risk in underground. In underground mining, you must be aware of potential rock bursts when such stresses overcome the tensile strength of such rocks. So particularly when you work in rocks with low Poisson's ratios, and mining engineers will know what the Poisson ratio of the rocks they are mining in actually are. In such rocks bursts are much more likely than in rocks with a high Poisson ratio. So this would be the Poisson's effect, and whenever you will work in a mine, and many of you might be working in mines, you should be aware what the Poisson's ratio and the Poisson's effect, what they actually are and what their importance is. So let's come to the next section, and these are parameters influencing the strength of rocks, and that is a very important central section that you should understand well, because it has implications for the broader understanding of the behavior of rocks and the deformation of rocks. The four important parameters we are going to talk about are the confining pressure, the pore fluid pressure, the temperature, and the strain rate. All of these features we have already covered in some form. Now let's discuss them again in context. The confining pressure. The confining pressure is correlated with depth. The deeper you are in the crust, or in the mantle if you want, the higher is the confining pressure. That is normally the least principal stress, and that increases with depth. Here we see a series of experiments run at different kinds of confining pressure, and the confining pressure is always shown here in these numbers, from 20 megapascals to 140 megapascals. Here we see the stress strain curves of these experiments. We see here the nonlinear stage 1 at the beginning, that would be closure of pore space, and then a long linear or near linear elastic episode of strain, which is normally less than 1%, followed by rock failure when the yield point is reached and we turn the curve into higher and higher strain, which would be permanent strain, either brittle or ductile failure. We see here at low confining pressures, and we are looking here at experiments carried out at limestone. At low confining pressures we find here rock failure at about 210-220 megapascals differential stress. The rock fails by brittle failure, and we see a very significant drop after the fracture is formed, down to a kind of a plateau with minor strain hardening here of sliding friction. So the frictional sliding here occurs at a significantly lower differential stress than the rock failure has occurred. With increasing confining pressure, we see in principle the same curve, but we see that rock failure only occurs at higher differential stresses. And we also see that the drop down to the level of sliding friction is a little bit smaller than here at 20 megapascals. And this trend continues. Increasing confining pressure increases the shear strength of rocks, because permanent strain, the rock failure, the yield point, is reached at higher and higher differential stresses. And we see also here the drop after rock failure is smaller, is becoming smaller, until we eventually come to a linear behavior, and this drop after rock failure cannot be recognized, is not there anymore. This happens at high confining pressure, and this is the transition from elastic into plastic flow. At these high confining pressures, limestone would respond by plastic failure rather than by brittle failure. The characteristic in such stress-strain diagrams is for brittle failure is this instant drop after rock failure, after fractures have formed. And obviously in the plastic ductile failure, no fractures are formed and therefore there is no drop. This feature we are going to discuss again in the context of the more stress diagram in Chapter 5. The pore fluid pressure. Let's have a look at experiments run in a sandstone here at low temperature with increasing pore fluid pressure. We see here the uppermost curve has a low pore fluid pressure. Here we see a high pore fluid pressure, and we can observe that rock failure here in the dry experiments that have a fluid pressure of 0 occurs in a very gradational way at from about 200 megapascals to 280 megapascals of differential stress, and then we reach some sort of strain hardening plastic flow in this barrier sandstone. If we increase the pore fluid pressure, we see that the curve here of more or less steady state or slightly strain hardening strain is reached at slightly lower differential stresses. With increasing pore fluid pressure, we see here rock failure at lower and lower differential stresses. These experiments here are aborted at rock failure. They are not carried on with sliding friction or with a continuous amount of strain as we see here in the first two experiments, but what we want to see here is rock failure occurs at lower and lower and lower differential stresses. So clearly increasing pore fluid pressure weakens rocks, and this is quite easy to understand because fluids do not have a shear strength. A fluid has a shear strength of 0, and if we inject and press more and more fluid into the pore space, then we will counteract the confining stress, and we will in fact have a lot of material, fluid, in the pore space that has no shear strength. It is our part of the rock, and if part of the rock has no shear strength, the overall shear strength of the rock will drop. The relationship with the confining stress in this context is important because the pore fluid pressure acts outward of the pore space. So a pore space with a fluid, if we increase that fluid pressure, we need to think about stress vectors that act in all directions outwards of this pore space. And that means they counteract the compressive stresses of rocks, and this has a similar effect like lowering the confining stress. We see here with low confining stress we have a lower shear strength of the rock, and this is a similar effect like having a high fluid pressure, which counteracts the confining stress. Also this we can describe in the more stress diagram, and we will see how dramatic the effect of increasing pore fluid pressure is on failure of rocks and shear strength of rocks. Temperature. Obviously temperature has an important effect because we know at low temperatures in the brittle part of the crust, rocks behave in a different way than in the high-grade metamorphic environment of the middle or lower crust under orogenic conditions, where temperatures might go up into the granulite facies of, for instance, 800 degrees. And obviously a rock, a silicate rock, or also obviously a carbonate, would respond under high temperatures in a different way to differential stress than under low temperatures. And here we see that illustrated. Here again, all other parameters kept constant, we see that a rock under laboratory room conditions 25 degrees might have a very high shear strength. So this rock is a very hard material. We see here rupture and failure occurs only at maybe 1700 megapascals of differential stress. When we increase the temperature to the lower green schist facies, this rock starts to deform permanently at maybe 1300, 1400 megapascals, and we get steady state flow here with some minor strain softening in this case. But what is important here, the yield strength is significantly lower than under cold conditions. We go higher into 500 degrees transition of the green schist to the amphibolite facies. Yield point is about 1000 megapascals, and then in the upper amphibolite or granulite facies we see that this rock has a much lower shear strength of maybe 500, or maybe only here at 800 degrees only 200 megapascals. And this is an important piece of information. Hot rocks tend to be much softer than cold rocks, and that means the upper crust has a higher shear strength than the lower crust if there are high enough temperatures. And normally that is the case, because you know the geothermal gradient of maybe 25 degrees per kilometer gives you in 10 kilometers about 250, maybe 300 degrees, and in 20 kilometers you would have 500 degrees. You will be in the amphibolite facies in the lower crust. Strain rate. We have talked about the strain rate before. If you deform a rock very fast, then it will have a higher resistance, a higher shear strength than if you do that very slowly, and also the way of failure might be different. We see here strain rates given in the as values per second. And here we see all these are experimental strain rates. These are much faster strain rates than strain rates that we typically observe in nature. You know that a natural strain rate would be something like 10 to the power of minus 13 or minus 15. And here we see the slowest strain rate here at the bottom is 10 to the power of minus 8 per second. So all this here is experimental, but still we can see the effect. If we have a very high strain rate, the yield strength will be much larger than the yield strength under low strain rates, very slow deformation here, say for the experimental field. All these here experiments are carried out on marble material at 5000 bars confining pressure and at 500 degrees temperature. At the strain rates of natural systems, so put a few orders of magnitudes on top of these strain rates to come to 10 to the power of minus 13 or 14, you will see that such a marble would have hardly any shear strength. The yield strength would be probably only a few megapascals. At 500 degrees, in natural systems, marbles are very soft material. Thank you very much.